Alright, thanks everyone, I did it. After 3 days of staring at a textbook and then scratching through many pieces of paper, finally did my first coordinate geometry proof. So, what I want to prove in this statement is prove that the diagonals of a rhombus are perpendicular to each other. That means that they meet at right angles. And if you know, when we're doing a coordinate geometry and we do lines, the main condition in order to show that two lines are perpendicular, which is this thing over here, is to show that their slopes are negative reciprocals of each other. Or rather, when you multiply them together, you get -1. So that's exactly what we're going to do here. I have my rhombus written down over here. I've put one vertex at the origin, so 0, 0. Another vertex at a point A0, where A is an arbitrary horizontal coordinate. I label another arbitrary coordinate, BC, over here, which is the horizontal length of this coordinate here, and C, which is the vertical height of this coordinate, or the height of this rhombus. So A you can think of as the length of a rhombus, because a rhombus is a quadrilateral with 4 congruent sides, but the angles might not necessarily be the same. So this side length is A here, same with this is A, and so it has a height of C. So this coordinate is B comma C, and finally this coordinate is A plus B comma C. And we can see this by, if we go and extend or draw a rectangle from here to there, we know that this horizontal length here is A, but we also know that this horizontal length over here is B. But by these two lines being parallel and these two triangles being similar, we can conclude that this horizontal length is also B. So this coordinate has to be A plus B comma C. Now, the main condition which we need to prove this theorem is true is to take the square of these two different distances. Yeah, don't even bother with like normal distance, because that's going to deal with square roots, which is a pain. But we all agree, hopefully, that in order to find the square of the slant length, what we want to do is we want to take the difference in the y-coordinates, add it with the difference in the x-coordinates, and those differences get squared together. So this guy over here becomes A plus B minus A all squared, and this gets added with, just C squared, because that's the vertical component. On the other hand, we look at the horizontal length, that's just going to be A squared, because A is the length of the rhombus, and that's going to get squared. But A minus A cancels out, and so we're just left with B squared plus C squared equals A squared. I'm sorry that this is scrunched up like this. Let me go and put it in a box. And now, if we manipulate this, we can end up getting that C squared equals A squared minus B squared. But that is the difference of two squares, right? So we can break that out into two factors being multiplied together, namely A minus B times A plus B. And this is where it comes in handy, because now we have to go and find the slopes of the equations of these lines. If you remember, slope is rise over run. We take the difference over the y-coordinates and divide it by the difference in the x-coordinates. So essentially a ratio. I have it written out over here that the slope of line 1, you take the point, the y-coordinate C, subtracted by the y-coordinate 0 here, that's at the top, and then get the x-coordinate A plus B, subtract by the x-coordinate 0 over here. That's all good. That simplifies to C over A plus B. For the slope L2, we expect, since it's going in this direction, that's going to have a negative slope. So I start from 0 here and subtract with C there. So I get 0 minus C. And I divide it by A over here, minus b, a minus b. So you get minus c over a minus b. Good. Now, all we just have to do is multiply those two slopes together. Slope L1 times slope L2. And that part I'm going to write it here. That's just c over a plus b times minus c over a minus b. But as you saw, that simply becomes c squared by the distance corollary up over here, this key guy over here. When these multiply, this becomes minus c squared at the top, and by this thing here, this becomes c squared at the bottom, which naturally becomes -1, as we wanted and expected. So we can finally conclude that when these lines intersect, they do so at right angles. And yeah, I'll tell you personally, coordinate geometry, or geometry in general, is just a thing which is so hard to do, especially at the early grade school days, because you just have to get used to using a straight edge, a ruler, and a compass, and making lots of sentence arguments in order to get this stuff properly, which is why it's so hard, because when we're at that age, I don't think we have the patience or will to want to do it. So I agree, it's an acquired taste in some sense, and it's quite hard, but you can do it. If you get it eventually, you can break it down into these. An extra challenge for you. I found what the slopes of line 1 and line 2 are. Now it's your turn to go and construct the equations of the lines using those general coordinates that I found out. Feel free to post the answers in the comments. I believe in you. It's hard, but you can do it if you put the effort. And on a last footnote, I've noticed a lack of coordinate geometry proofs being listed systematically on how to do them. I think it'll be a good resource to have them more online. What do you think? Please feel free to let me know in the comments as well. Otherwise, please subscribe, and until then, I hope you have a wonderful day.